start it over. First couple of minutes is always scrap. But anyways, so welcome to the last session of the DSP part. So we actually have the 6 exercises, 6 parts on this DSP part of the course. And we have gone through signals, systems, responses, the system control, a brief introduction to system control, that is, and then filter design. Actually, I have been going through the exercises and have done overall quite a nice job. In average, as soon as Janne will update the scoreboard, you should see your points, what you have scored this far. And okay, but anyways, so today's topic is the last one, but not the least one. It's about embedded systems, which is actually the topic of the 15 credits course overall. So we have gone through 5 topics which are more or less general, which basically are okay for any system or any the discrete time system, meaning digital system, and actually also true if you have a floating point on the unit on your platform. So practically, this last topic is about how about if you have a smaller microcontroller or a controller which has only the this fixed point routines, meaning integer calculations. Of course, when you are using some, say, more advanced language like C and use a program, you can put floating point numbers even in 8-bit processors, but all the floating point calculations will take a lot time to do it on 8-bit processor. But if your system is natively a fixed point system, meaning integer arithmetics, then you are dealing with some rounding errors. And the embedded systems part of this DSP theory is about rounding errors and how they affect the system performance. Okay, and performance actually comes from here. So on digital signal processing, if you are doing filters or some, say, control logic, control systems, you are dealing with multiply, accumulate operations. So actually, these the control systems are just closed loop on the filters, so to speak. So they are in one sense, they are just as any other filter in the world. It has a controlling input, and then there's a feedback, and the controller actually is just trying to compensate whatever these say nonlinearities or some bad features about the plant itself. So basically, controller kind of makes. Okay, your voice sound bad. This is my headset, so it should actually be good. Can you hear me better? Any better now? Or worse? Okay, nobody's complaining. No, good. Wow. Just a moment. Let's try.
Actually get more, it might get more the surround noise. Better? Any better now? Or can you hear me at all? Okay, it's better. So I turned to my laptop microphone. Strange. This has been really great this far. But anyways, so performance comes actually from the how many multiply accumulate operations you need to do. So practically, for example, this the FIR calculation has nothing more than just multiply accumulate operations. Meaning accumulate is summing on the top of the previous sum. So you start with B0 times x of n, that's the initial value. Then you just start adding B1 times x of n minus 1 on top of that and that far. So practically the multiply accumulate operations are the key factor on these performance calculations. And when you're talking about the digital signal processors which are specially designed for digital signal processing applications like filtering or control, they have optimized instructions for multiply accumulate. So usually there are actually MAC operations on those digital signal processors. Some ARM processors do have a MAC unit, but not the one what you are using. You have the ARM Cortex M3, which does not come with the, it doesn't have floating point, and it doesn't come with the MAC unit either. Some more advanced ARM processors actually do have those, but you're out of luck. Which basically means if you want to make the, say, high performance system, meaning really fast control loop, which doesn't usually make any sense. But anyways, if you want to do something fast on that processor, then you need to do everything on integer arithmetics. Okay, so, but anyways, there's the code for doing the direct from finite impulse response system calculation. So practically, there's such data pointer stuff there on the beginning. Shall I do the pointer? Yeah. So data, the pointers, and then you have for loop for the length of that length of the FIR, and just go through the terms B and X, multiply those together and sum those to the next next value of the output. So that's part of a function which actually calculates a block of data at once. Okay, so MAC. So MAC in embedded processor is highly dependent on the processor architecture. Floating point implementation coding would be easy, but okay, unless you have a DSP block on your system or floating point block of your on your system, fixed point gives you much better performance. And actually, why all processors don't have the floating point unit is because it takes about the same amount of silicon as the rest of the processor, including all the memories and such. So it's actually a hog when you go to the, so it basically doubles the price of that processor. But anyways, so modern processors, they usually have MAC. Okay. But the ARM processor is not that modern. Or actually, there are these later versions of ARM. They have processors which has the Mac. And if you have a digital signal processing application, you should actually go and select a processor which has the Mac. And if the money is not an issue, then also the floating point unit there, since, well, the development cost will go down. Okay, if you go to the software floating point arithmetic with the single precision floating point on 8-bit processor, actually may take 1,000 to 2,000 instruction cycles to operate. So, okay, with 1 MIPS 8-bit processor, when usually are about 1 MIPS. So one single Mac operation, meaning multiply and accumulate, would take 2 milliseconds, which may be way too much time to calculate compared to a 8-bit Mac. If possible, that would take only about a few microseconds. Yeah, there are some fused multiply acceleration, so special hardware to do floating point in some processors, but then actually on really processing intensive the intensive operations, basically, then you would probably want to have a digital signal processor to do the these digital signal processing tasks. And as a matter of fact, it has been now for several years, or I think more than 10 years, that computers, they actually use the graphics processor for as a DSP. Since basically the graphics processor, what it has this special RAM that you just can feed the RAM with the information, and then a processor grabs it there at the same time as you're writing. Okay, that's a special kind of RAM there, but what is processing it is some sort of digital signal processor there. What is Mac? Mac, actually, that's the multiply accumulate. So it calculates the, so multiply accumulate, so it calculates this sum. But if you have an 8-bit processor and using floating point numbers, then you need to do everything on software. All the calculations on software. There is no floating point operations at all on the instruction set. There are only the multiply of integers and basically and adding, subtracting integers. So floating point must be done with some software manners. That's usually, that software is generated by compiler if you are using higher language like C language. Okay. Quantization of parameters. There's comparison of 3 different quantization levels. So now we are talking about quantization of the filter coefficients. This far, you have been calculating everything in floating point accuracy. In MATLAB or Octave, it uses double precision floating point, which is pretty good up to, say, 10th degree filters, the direct form filters. Okay, when you have to start doing everything on integer arithmetics, then the 16-bit precision on these coefficients actually means that your this passband already starts distorting. Stopband is usually quite okay. So first one, usually what is degraded performance is the passband. When you round more down to 8 bits, then you basically, this is not usable anymore, I would say. So it has attenuation there, and the cutoff frequency has been moved from 400 Hertz to 200 something. And then, okay, the transition bandwidth is wider. So it's not the same filter anymore. It doesn't match the requirements anymore. So that's what happens when you quantize the filter values, coefficients. So meaning, okay, I will, maybe I should actually show you what it means right now. Yeah, I think I need to draw you something. Okay, basically it's the same thing as we talked in the on the first lecture about signals. But anyways, maybe I can actually give you some. So if we have a, how to describe this one on drawing? Okay, I think I will leave this one to later. So basically what we are doing to get these integer numbers from filter coefficients, we are first multiplying, so adding gain to the whole system so that we can actually get those into meaningful values. Say if we are, if we have 8-bit signed integers, for example, it means that we have values from between plus minus 127 that we can use. So basically, we first to do the calculations on, say, 8-bit integer values, we first scale the filter so that these numerator coefficients and denominator coefficients fit good on that 8-bit accuracy. So it's the same as your gain of small signal, so your A to D converter can do the job. We do the same thing now for the coefficients for the same reason. We want to have as good accuracy as possible. And then it's integer arithmetic, so we round the numbers. And that rounding error actually then causes bad things for the filter. And this is exactly what happens, for example, in this particular elliptic filter, and the filter performance will go down because of the rounding errors on calculations. Okay. All right, system combinations. We will actually need some systems combinations, the cascaded systems, parallel systems, feedback system, especially for this reason. Second order systems. This I can actually explain with annotation. Let's take text. Think of the, was it, now I don't remember anymore, what is the name? Was it Fibonacci? Fibonacci's triangle. we have the, oops, let's see. Okay, does it ring a bell? So practically we have this 3, 3, 1. So when you have a calculating the 1, 4. Okay, what is the middle value? Is it 8 or 6? Oh, yeah, of course. 4, 1, and so on. Okay, so practically, then if we have a system where the h of z is simply z minus 1 to the power of some value k. Okay, so if k is 2, then we have z squared plus 2 times z plus 1, okay? And then if we have k is very large, then we have a very big number here at the somewhere after say 10 or so. So that is already in different order of magnitude as than basically the second order system. So in here, our numbers are on the same order of magnitude. In here, down on the line, we have some of these are starting to have problems that at the middle we have, say, actually let's put there some numbers, 1, but then at the middle, there might be actually something like 100 or so, or 1,000, well, 100 or so. Okay. So basically, these are in 2 orders of magnitude different. And when we are having a direct form filter, meaning this one, everything is in one filter. Everything is on one filter, say 50th order FIR filter. Okay, we have the order of big difference on order of magnitude. When we scale these numbers to fit that, scale the numbers to for that quantization, we actually start losing small numbers. On 8 bits, this would still work, but this could be, say, 200. And we scale it down to fit all of that 8 bits. So this one will be less than 1, meaning 0. So we are starting to cancel the small terms, and also all the terms will have a bit of rounding errors. And every single term actually matters. So how to avoid this one? Well, we can avoid this by breaking this kind of higher order systems by second order sections. Why second? Well, that's because you can then make zero pole pairs with complex conjugates and use each of those as separate small system in between. Okay, so second order system is the way to go, especially, well, this was FIR example, but especially for higher order IIR systems. See, the IIR systems, those are nasty. If your pole is close to the unit circle, as in higher order system you usually have, this rounding error actually can can actually flip that the pole to wrong side of the unit circle, meaning the system becomes unstable, meaning unusable. Okay, so that is one danger of the higher order systems, if they are calculated as the direct form, meaning just everything on one block instead of bringing it to cascaded second order blocks. Okay, clear drawings. Right, so we want to use second order blocks. Okay, there's an example of what second order block actually does for FIR filter. Okay, instead of direct form. So floating point is here the blue one, which is actually behind the red one. 8 bits is the direct form, meaning that everything is calculated here. How you are dealing with error in second order system. Okay, on the second order systems, you don't have that much errors, since these coefficient values are basically about the same value. The order of magnitude is the same. So the relative error will be much, much smaller. And how do you deal with it? Well, you just leave it there, since, well, there will be some errors. You are making some choices here. If you are shooting for performance on the discrete time systems without floating point acceleration, then the only way to go is to basically select the word length that fits your requirements. But anyways, it's not that bad actually. When you have, for example, FIR system here, then, okay, wouldn't first order systems have even less errors? Yes, but you cannot do with the first order systems if you have a complex, the zeros and poles. You must actually pack them on the complex conjugate pairs. Otherwise, you are calculating with complex number the coefficients which don't really make sense. So they must be complex conjugate pairs. Okay, so 8 bits direct form, the green one, okay. And then we have basically the FIR system will suffer only on the stop band attenuation. And by the way, that 40 dB is kind of what you would expect. 40 dB is about the this signal to quantization noise ratio of 8 bits data. So practically, this is the noise floor here. So, okay. But if you break this FIR filter into second order sections, then you get that required attenuation back. So, okay, less calculation errors. On IIR, usually the stop band is okay-ish because these poles are dominating this the amplitude response. They bring gain, extra gain. So if you have small the increase in or decrease in attenuation, usually it's less than what the gain does. But anyway, so practically this is similar comparison. The floating point is our desired the behavior. Then we have 8 bits which gives us that funny looking with the passband, which is not anymore, doesn't look like the filter we are looking for, but breaking into second order systems. This error here is practically just the gain of the system has, overall gain of the passband has changed a bit. So it's higher, a couple of dB higher, but well, that's the easiest possible thing to fix on any system. Even with the 8-bit arithmetic, you can multiply it with bigger number and then divide it with another number, and that's how you gain this gain. This gain disappeared. DC gain is different. So here, the floating point is DC gain. Oh, DC gain. Yeah, DC gain here. It's not disappeared anywhere. So it's just, it's different. About, is that 5 dB? 5 dB in between. So rounding error actually also gave a little bit more gain to the system. But the filtering characteristic remained about the same. Still usable. Okay. So practically, this was the shortest lecture during this course. But okay, it has, yeah, I was fast this time. Don't worry, I will take some more time on the exercise. It's a, say, heavy-ish. Unless you have MATLAB. I noticed that some of you are using MATLAB. Excellent, excellent, excellent. That's the real professional tool. So if you ever get into the job that where you need to design some digital signal processing stuff, including control systems, ask your employer license for the MATLAB and the necessary toolboxes. That's what is supposed to be used in professional life. Why we are using this, why I am using this Octave instead is because our campus license does not allow teachers to have, actually those licenses should be used only within the premises. Okay. And on the other hand, teaching the basics might be a little bit better if I just show you how to do it on, say, bit by bit. But MATLAB has the tools to actually go through some of that stuff, like selecting which rounding to use, and it gives you all the necessary points there. Okay, so, but anyway, so what is the these rounding errors or embedded systems DSP all about? It's about optimizing the performance for multiply accumulate. So this MAC was before the MAC address called, what is it called? MAC is also on the, all computers have that, is it 64-bit code for the network use. This is not the same MAC. This is multiply accumulate operations. And this was invented in the 70s. We didn't have internet that time. Okay, so Mac operations. Some it's highly processor dependent. You are using that ARM processor on LPC 1768, which is Cortex M3, which does not have a floating point, native floating point, nor DSP blocks. Okay. quantization of parameters is then required, or if you have slow sampling rate, you can actually use software floating point calculations. And okay, you can actually measure the performance also, how fast it goes. One way to go is basically just test how fast your system is doing maps, then do the simple arithmetics and see if you can use floating points or not. My preference is always to use floating points if the system just can do it. Okay. This you should do anyways, is to break everything on second order blocks. It actually also helps even if it is even if the system is floating point system. So basically it helps even there. Say if you have an IIR system with order number of higher than 8, even double precision floating point numbers may not be accurate enough for the calculations. Okay, on FIR is okay. Usually the passband is okay, even with this when you are studying to quantize the values, the filter coefficients, stop and attenuation degrades. But when you go to the second order systems, then basically you can get that fixed. IIR systems, the problem is that you may actually you are moving the location of poles, which means that they can go even on the wrong side of the unit circle, meaning a useless the system of useless unstable system, but even if it doesn't, then it usually moves the angle of those poles, and then you are moving this basically the ripple on different place, meaning that it degrades that performance a lot on passband performance, which is actually worst what can happen. Okay, good. So how about if we have a break until 11:50? Oh, actually, let's make it 12 o'clock. Let's continue at 12 o'clock sharp. Unless you have more questions. Okay, it seems that there are no questions. I stop recording.